Hello friends, I welcome you in lecture number 5 on Taylor and Maclaurin series. In this lecture we will do some more examples on how to determine Taylor and Maclaurin series using standard Maclaurin series. So we just recall, we know that Maclaurin series expansion of this function is given by this geometric series sigma z to the power n is from 0 to infinity, and the radius of convergence of this Maclaurin series is absolute value of z less than 1. That means the series on the right hand side converges to this function for all values of z which are in the open disk with center 0 and radius 1. So we are going to use this standard Maclaurin series known as geometric series of this function, but we will keep in mind that we must have this quantity in such a way that its absolute value is less than 1. So with this in mind we consider this example. So here we are asked to find out Taylor series of this function f of z equal to 1 divided by c minus z in powers of z minus z0. That means center of the Taylor series is z0, and it is given that c minus z0 is not equal to 0. Now as we know, if we want to find out Taylor series about point z0, then if we want to apply Taylor's theorem, then we have to find out all these values: value of function at z0 and value of derivatives of function at z0. So that is one way we can use Taylor's theorem to find out Taylor series of this function with center z0. But we are not going by Taylor's theorem, we are going to use Maclaurin series expansion of this function 1 over 1 minus z. So first we have to express our function in this form 1 over 1 minus something. So let's try to express our function in that form. So for that, because we require series in powers of z minus z0, first I consider addition of z0 and subtraction of z0. So I rewrite this term as c minus z z0 plus z0, and we require z minus z0. So for that we can combine these two. So we combine this two, c minus z0, and this minus z plus z0 can be rewritten as negative and in the bracket z minus z0. So you can see c minus z0, and if I take negative sign inside the bracket, I will have minus z plus z0. Now again our function is not in this form, we require 1 minus something. So instead of c minus z0, we must have 1 minus something. So what we can do is we can rewrite in this way. We take c minus z0 common, and here we rewrite this as z minus z0 divided by c minus c0, c minus z0. Instead of c we have z here, and we are given that c minus z0 is not equal to 0. So there is no problem in writing this c minus z0 in the denominator. So it is defined. So now we are able to write our function in this form 1 over 1 minus z. Instead of z, now we have this quantity z minus z0 divided by c minus z0. So now we can use that standard Maclaurin series expansion of 1 upon 1 minus z. We know that 1 over 1 minus z is nothing but sigma z raised to n. N runs from 0 to infinity, and this is valid if absolute value of z is less than 1. So using this standard expansion, we are using this standard expansion for this quantity. Instead of z, we have z minus z0 over c minus z0. So in this series, we will replace z by this z minus z0 divided by c minus z0. So we have sigma n equal to 0 to infinity z minus z0 divided by c minus z0 to the power n. And this series is valid if absolute value of z is less than 1. So here instead of z we have z minus z0 over c minus z0. So this expansion is valid if absolute value of z minus z0 over c minus z0 is less than 1. Now this we can rewrite as our function is 1 over c minus z. So we write value of function here 1 over c minus z. This is equal to 1 over c minus z0 sigma n equal to 0 to infinity, and here this we can rewrite as nth power of z minus z0 divided by nth power of c minus z0, and this quantity is nothing but absolute value of z minus z0 divided by absolute value of c minus z0, and because c minus z0 is different from 0, this absolute value is non-zero, and therefore again we can rewrite this as if we can take this 1 upon c minus z0 inside the bracket because it is independent of n. So we obtain z minus z0 to the power n divided by c minus z0 to the power n plus 1, and this we can rewrite as absolute value of z minus z0 is less than absolute value of c minus z0. So this is the Taylor series of the function 1 over c minus z in powers of z minus z0, which is valid in the open disk with center z0 and radius equal to absolute value of c minus z0. And because c minus z0 is different from 0, there is this radius is positive. So in this way, without applying Taylor's theorem, we are able to find out Taylor series of this function in powers of z minus z0. So we consider one more example. Here we are asked to find out Maclaurin series of z plus 2 over 1 minus z square, and also we are asked to write down the radius of convergence of Maclaurin series which we will obtain. So first we write down given function f of z is nothing but z plus 2 over 1 minus z square. So here also we are not going to use Taylor's theorem, that is we will not calculate derivatives at z equal to 0. Instead we will write down our function. We will try to express our function in this form. So for that, if we observe in the denominator we have 1 minus z square, that I can write as 1 minus z times 1 plus z. So if you observe, this is a rational function in which degree of numerator is 1 and which is less than degree of denominator. So this rational function is proper rational function, And as we know, if we have proper rational function, then we can always write it as a sum of partial fractions. So first we try to express our function as a sum of partial fractions. So in the denominator we have two linear factors, 1 minus z and 1 plus z, and because this rational function is proper, we can always represent our function as a sum of two partial fractions, a divided by 1 minus z and b divided by 1 plus z, where we will determine these constants a and b. So for that, first we multiply this whole equation by 1 minus z into 1 plus z. So we obtain z plus 2 equal to a times 1 plus z plus b times 1 minus z, and we give this number 1. Now corresponding to 1 minus z, we know that 1 minus z is 0 if z equal to 1. So first we put z equal to 1 in equation number 1. So on the left hand side we have 1 plus 2 equal to a into z is 1, so 1 plus 1 and plus 0. So therefore 3 equal to 2 times a, so the constant a is nothing but 3 by 2. Similarly 1 plus z is 0 if z equal to minus 1. So now we put z equal to minus 1 in equation 1. So left hand side is minus 1 plus 2, here minus 1 plus 1 0, and b into 1 minus minus 1, that is 1 plus 1. So this is 1, and here we have 2 times b. So b is nothing but 1 by 2. So we substitute values of a and b in this f of z. So therefore f of z equal to z plus 2 upon 1 minus z 1 plus z. So here a is 3 by 2, so we have 3 by 2 times 1 over 1 minus z, and b is 1 by 2, so 1 by 2 times 1 over 1 plus z. So now we can observe we have this function 1 over 1 minus z here, and the function 1 over 1 plus z can also be written in this form. We replace 1 plus z by 1 minus minus z, and now we use the Maclaurin series of 1 over 1 minus z. So it is nothing but sigma n equal to 0 to infinity z raised to n plus 1 by 2 times sigma n equal to 0 to infinity. Now instead of z we have minus z, so here we write minus z raised to n. Now first series is valid if absolute value of z is less than 1, and second series is valid if absolute value of minus z is less than 1. But we know that absolute value of minus z is nothing but absolute value of z. Both are always equal. So both the series in the summation are valid if absolute value of z is less than 1. And of course we are using this standard Maclaurin series expansion, so we have to mention in the bracket whatever result we are using. So we are using the Maclaurin series expansion of 1 over 1 minus z. Now we just have to rewrite, we can combine both the summations. Here we have 3 by 2 into z raised to n plus 1 by 2. We take 1 by 2 inside the bracket, and minus z raised to n can be written as minus 1 raised to n into z raised to n. and both the series are valid in the open disk mod z less than 1. And again we can combine these two summations. Both are from n equal to 0 to infinity, and we have z raised to n also, so we can write 3 by 2 plus minus 1 raised to n by 2, that we can rewrite as 3 plus minus 1 raised to n divided by 2 into z raised to n, and this is valid in the open disk mod z less than 1. So we obtain Maclaurin series of given function, and this Maclaurin series is valid in the open disk mod z less than 1. Therefore the radius of convergence is r equal to 1 of Maclaurin series is r equal to 1. So in this way we can find out Maclaurin series of this type of proper rational functions using standard Maclaurin series, and we are first converting this proper rational function as a sum of partial fractions, and then we are using the standard Maclaurin series of 1 over 1 minus z. So I stop here. In the next session we will discuss some more examples on this Taylor and Maclaurin series. I hope you like this lecture. Thank you very much.